All right. So it seems that my storage are already full, I guess. So that is why it doesn't want to record that storage. Well, anyway, so sorry for the delay. So can you guys see my screen now?
Yes, sir.
Yes, sir.
All right. So nasa Facebook pa. Anyway, so we're going to talk about module 5 and 6 for today. So as you guys can see, this one is only 14 slides, and then the other one is, if you guys have checked that one already, that one is only 10 slides. So this will only take maybe 2 meetings. So part 1 and part 2. Okay, so let's start now without a further delay. So module 5 will be about superposition theorem, okay, DC network analysis. All right, so here's the definition of a superposition theorem. So superposition theorem is one of the genius way, to simplify or solve a complex subject and simplifies it in a way that makes perfect sense. Okay, so like the case, I mean the Kirchhoff's law, the Maxwell or the mesh current method, and this one superposition theorem is one of the best way to eliminate or to simplify complex circuit into in a very simple manner, or a very simple circuit. So the strategy used in superposition theorem is to eliminate all but one source of power within a network at a time. So using series or parallel analysis to determine voltage drops and or currents within the modified network for each power source separately. So when we say superposition theorem, this one is perfect if we have a lot of sources. So if we have, let's say, more than two sources, one voltage source and then one current source, or it could even be, two voltage source or two current source, so any of those two. Okay, so as long as it's more than one source, then superposition theorem is one of the perfect theorem that you can use to simplify it in a simple circuit. Okay, so then once voltage drops and or currents have been determined for each power source working separately, the values are all superimposed on top of each other, so added algebraically to find actual voltage drops or currents with all sources active. So meaning, as you guys can see right here, we will eliminate everything and then we will retain one voltage source. So let's say if we have two voltage source, so we're going to have two computation for that. So we're going to eliminate the other voltage source for now, and then we're going to solve the other voltage source. So that's your first computation, and then vice versa. So for the second computation, you're going to eliminate the first voltage source, and then you're going to retain the second voltage source, and then compute that, get the voltage drop, get the current, and then once you've got the results of those two computations, you can now combine them, okay, as one. So once you have combined them, we call that one superimpose. Okay. So for you to have an idea, let's proceed to this example. So one thing that I would like you guys to notice is this example was actually used in our mesh current method, or the Maxwell loop method. So let me just show that one to you. Maxwell. Oops, not this one. This is your lab. All right, so we have used this one before already in Maxwell. So as I guys can see, you have 28, 4, 2, 1, and then 7 volts, which is the same with this example, 28, 4, 2, 1, and then 7 volts. So we are going to prove that, just by using superposition theorem, okay, we can also have the same result, okay? So let me just show to you guys the result here. So we have here 5 amps, okay, on this side, and then we have here negative 1 amp, okay, and then if you're going to combine them, we have, where is the final? Right here. So 5 amps here, 1 amp here, and then 4 amps here, okay, and then of course their individual voltage drops, okay. So we're going to prove that one using a superposition theorem. All right, so let me just minimize that one for now, and then let's take a look on this example. So again, we have two sources, so superposition theorem is perfect for this example. So we have 28 volts and then 7 volts, and then we have three resistors. So since we have two sources of power in the circuit, we will have to calculate two sets of values for voltage drops and or currents. So one for the circuit with only 28-volt battery in effect. So as you guys can see, we have only considered the left side part for now, or the left side voltage source, and then we have eliminated the other voltage source. Okay, so here's what you can do. If it's a voltage source, okay, where is that one? Okay, here. So if it's a voltage source, all you need to do is short that one. Okay, so in other words, we call that one make, wherein if you're going to make it, of course, it's now short. Okay, but if it's a current source, okay, all you need to do is the opposite. Okay, so if it's short in a voltage source, then in current you need to break it. Okay, so you just leave it open. But since this one is voltage source, so yeah, 7 volts is voltage source, so just short that one. Okay, as simple as that. That's the only thing that you need to do to the other sources. All right, so yeah, that's your first step, and then having now this circuit. And here's now the result. So let's have our own solution regarding with this one. So let me just get this one. Okay, so in here, the one that we are looking for, so find I1, I2, I3. So those are the individual currents, and then we also need the voltage drops of those resistors. So VR1, VR2, and VR2. Okay, so we need to solve those six. So let's start. So the first thing that we can do is actually find the total current. Okay, so finding the IT. So in finding the IT, as you guys can see, it's super simple. Just get the parallel of this one R2 and R3, and then you can now combine that one or add that one to this R1 since they are now in series. And then you now have the total resistance. So from there, we already have the total voltage and then the total resistance. Then we can now solve for the total current. So the formula for the total current is IT is equal to VT divided by RT. All right. So in here, if I will simplify this one, let me get another copy. Okay, but let me make this one smaller. So what I will do is I will now, add the R2 and R3 with each other, the computation of parallel. So I will delete this one, okay, and then this one now will become R2 parallel to R3. Okay, so this one now is not 1 ohm anymore. But for us to be able to get the value of this R2 and R3, so we need to solve for that. So R2 parallel to R3, okay, wherein we only have two resistors, so we can use this formula wherein we have 2 times 1 divided by 2 plus 1. Okay, am I correct? So were you guys able to follow on how did we get this expression right here for the parallel of the R2 and R3? Okay. How about the others? Just give me a thumbs up if you guys were able to follow up to this point. And if you have a question, so feel free to ask feel free to raise your hand anytime. Okay. So in here, just use your calculator and you will get 2 times 1 divided by 2 plus 1. So we will get 0.66667, or you just simply say it's 67, 0.67. Okay. So this one is ohms. Okay, I hope You guys can see this one. All right. So right here, we already have the value of R2 and R3, okay, which is 0.67. And as you guys can see, they are now in series. So R1 plus R2 parallel to R3. So that is the uh, result for our total resistance. Okay, RT is equal to R1 plus the value of the R2 and R3. So in here, R1 is 4 ohms, and then the value of R2 and R3 is 0.67. Okay, so for our RT, we have here 4.67 ohms. Okay, so were you guys able to follow up to this point? And how did we get 4.67? Okay, it's good. And then since we now have total resistance, then we can now solve for the total current. So Vp is 28 volts, and then RT is 4.67. So 28 divided by 4.67 is 5.995 or 5.99. Or we could just simply say it's 6 ohms, okay, to be exact. Okay. So you will know later on why did I put here 6. So you could put here 5.99, so they are just the same. But I'll just choose 6 because that is the one that we have, okay, in this table. Okay. So we have 6 ohms, 6 total current, okay, which is this one. All right. Why ohms? That is the reason why I'm confused. This one is 6 ohms, okay, not ohms. All right. So from here, we could already see that, we have here 6 amps. And then right here for the I1, okay, this one is now having a current of 6 amps. So I1 is already answered, okay. But at this point, okay, so we don't know since they will split, okay. Some of the current will go to R3 and then some of the current will go to R2, okay. So what we need to do for us to be able to solve the VR1, VR2, and VR3, okay, so we need this formula first. So VR1 is equal to, so since we are looking for the voltage drop on R1, so we need the I1 times the R1, okay, wherein I1 is already 6 amps, and then R1 is 4 amps. So the voltage drop across R1 is 24 volts. Okay, so VR1 is now already answered, 24 volts. There you go. Now, so as you guys can see right here, at this point, we have a voltage drop of 24 volts. So 28 minus 24, so you'll get a potential voltage, okay, of 4 volts. So we could say that this is our node A. So in order for us to get the voltage that that is remaining after passing through this R1 right here, so we could say that VA or voltage at node A is equal to total voltage minus VR1. Okay, wherein VT is 28 and then VR1 is 24. Wherein we will get 4 volts as our potential voltage after passing through this voltage drop. So that is why this node A right here is equal to 4 volts. So we already know that, some voltage will go here, some voltage will go here. But if you guys are going to take a look on this one, they are actually in parallel. Okay. So again, in parallel, whatever is the voltage that is passing through here is the same or equal with the voltage that is passing through here, as long as they are in parallel with each other. Okay. So that is why we could already assume that VR2, okay, is equal to 4 volts, and at the same time, VR3 is equal to 4 volts. Because we already know that, we have 4 volts that will pass through here, and then 4 volts another that will pass through here, and then going back here will be 0. Okay. So we could also apply the concept of KVL. Okay, after passing through all of those loads or resistors, as soon as it goes back to this original source, it is now equal to 0. Okay, so were you guys able to follow on how did we get this VR2 and VR3? What about the others? Again, it is a concept of parallel. Okay, so if we don't have this R1 right here, then we are sure that we have 28 volts passing through here and then 28 volts passing through here. But since we have series connection right here, then of course we have to deduct that voltage drop in here. Okay, so we already have answered the VR1, VR2, and VR3. Okay, which is 4 volts and then another 4 volts. Then the one that we are now looking for is the I2 and I3. Okay, so for the I2, so it's now very simple. Okay, so we need the voltage, say VR2 to make it consistent. Voltage across R2, and then of course, uh, I2 R2, yeah, the resistance. So VR2 is 4 volts, and then for the R2 we have 2 ohms. So 4 divided by 2 is 2 amps. So that is now the current that is flowing right here. Okay, so 6 amps and then 2 amps. And then from here, just by using KCL, we could already see that, so we have 6 amps here and then 2 amps here. So the remaining 4 amps will go to R3. Okay, but just to show it using a Ohm's law formula. So let's do that one. So I3 is equal to VR3 divided by R3. So VR3 is 4 volts and then R3 is 1 ohms. So there you go. So 4 divided by 1 is 4 amps. Okay. So if you're going to check this one using KCL at node A. Okay. So we have here the I1 that is entering this node, and then I2 leaving, and then I3 leaving. So I1 minus I2 minus I3 is equal to 0. So if you're going to, transpose this I2 and I3 on the other side, you will have this kind of expression plus I3, okay, which is actually correct. Okay, so I2 is 2 ohms and then I3 is 4 amps. So 2 plus 4 is 6, which is equal to our I1 or I total. So there you go. So were you guys able to follow? And how did we get those individual currents and individual voltage drop? Okay, very good, Mr. Labsan. How about the others? Anyone who has a question? Okay, very good, Mr. Awas. So very good, Mr. Ramos. Very good, Mr. Mendoza. Okay, very good, Mr. Panicala. Agustin. How about Mr. Mina? Mr. Arad? Okay, very good. Mr. Francisco. Miss Chelsea. Miss Ventura.
Yes, sir.
Okay. So I'm clearing the things that you might have a question right now because I am now going to erase this one. Okay. So I won't be able to explain this one anymore since we don't have enough space, and then we will proceed now on the second set, which is solving for the 7 volts. Okay, so I hope everything is clear because I will not explain this one anymore. Okay, so if you're confused, so you can always uh, watch this recorded video, and yeah, just watch it again and try to analyze it again. Anyway, so let's try to compare now our answer to this table right here. Okay, So maybe I'll just put it right here. All right. So we have here the voltage, the current, the resistors, and then we have here the R1, R2, R3, so individual currents, individual voltage drop, and then we have here the parallel uh, result of the R2 and R3, and then the total results of those. So let's start right here on the total. So we already have the 28 volts as our total voltage. And then we have here the 6 amps as our total current. And then we have here the 4.667 as our total resistance, which is this one. Okay, so only here yet get the 3 decimals, but in our case, we only get the 2 decimals. Okay, and then for the parallel value of R2 and R3, which is 0.67, okay, which is just the same with this one. And then we have here the uh, what you call this one voltage, okay, that is passing through this R2 and R3, which is 4 volts. So it's the same. And then, of course, once we have combined them, so we are now in series connection. So as you guys can see, we now also have here 6 amps in total. Okay, so 6 amps for the R1, and then 6 amps for the R2 and R3. Okay, so 6 amps for the R1. And then if you're going to separate those, so we have here the 2 amps for the uh, 2 ohms, and then 4 amps for the 1 ohm. Okay, so yeah, that's it for the current. And then for the total voltage, I mean the voltage drop rather, so we have here 24 volts across R1, so that's the voltage drop. And then up to, reaching the R2 and R3 since they are in parallel, so it's 4 volts per volts. And then we have here the value of resistance. So R1 is 4 ohms and R2 is 2 ohms, and then R3 is 1 ohm. So yeah, there you go. This is just the summary of our answers, okay, in which they are the same. Okay, so before I will delete everything in here, so do you guys have a question so far? Anyone who has a clarification? All right, so I guess none. So let me now erase this one, and then let's now proceed to the second one. Okay, so in here we are now going to deal with the 7 volts. Okay, so here's the result for this one. So the same, you're going to find the individual currents and then the individual voltage drops. VR1, VR2, and VR2. Okay. So the same process. So the first thing that we need to look for is the total current. Okay. So IT is equal to VT divided by RT, wherein in here, RT is equal to the R1 parallel to R2 plus RT. Okay. So let me just again create another simplified version of this one. Oops. So I will delete this one to make everything in series connection. Okay. And in here, this is not R1 anymore, but this one now is R1 parallel to R2. R1 parallel to R2. Okay. Okay, let me try to use this extractor instead of using, paint. All right. So in order for us to get the value of R1 and R2, so again, we need the formula. No, it's difficult to have a numerator and denominator regarding this one. Anyway, let's try. So 4 times 1 divided by 4 plus 1. Okay. So in here, if we are going to simplify that one, I think it's much more difficult to use this one. Anyway, okay, so 4 times 1 is 4. and then divided by 5. 4 divided by 5 is equal to 0 0.8. So this one is equal to 0 0.8, okay, ohms. Okay, so that is now the value of your R1 and R2, 0 0.8. So from here, you can now combine the R1, R2, and R3 for you to be able to get the R total. So R total is equal to R2 parallel to R1 parallel to R2 plus R3, wherein R1 parallel to R2 is equal to 0 0.8 and the R3 is 1. So for the R total, we have here 1.8 ohms. Okay. So in here, we already have the value of R total, so we can now solve for the value of total current. So V total is 7 volts. So 7 divided by 0 0.8 is equal to, so we have here 8.75 amps. So I hope you guys are also checking my answers using your own calculator. Okay. So were you guys able to follow up to this point? 8.75 for the total current. Okay, very good. So as you guys can see, so we have here the I total, which is now equal with our I3. Okay, I3 is equal to 8.75 amps. Okay, so now we can now actually solve for the value of BR3 since we now have the value of I3. Okay, ah, all right. So very good, Mr. Agustin. So why did I only write here 0 0.8? Because, what we write here is 1.8, not 0 0.8. So thank you for that one. So this one is not 8.75. Okay. Very good, very good. And this one is not 0 0.8, but this one is 1.8. And of course, this one now is not 8.75. So 7 divided by 1.8 is equal to 3.88889. Or we just simply say that this one is 3.89. Okay, so we still have 2 minutes left. Okay, which is now the same with our I3. Okay, I3 is 3.89 amps. Okay, are there more questions? Okay na, teka lang. 4 times 2. Oh, I see. See, I have a lot of mistakes. So thank you, Mr. Agustin and then Mr. Mina for, where is my cursor? Right here. So this one should not be 4 times 1, but this one should be 4 times 2 and then 4 divided, divided by 4 plus 2. We have a lot of mistakes. Okay, let me erase this one, and also this one, and also that one. Okay, so in here, and of course this one also. So here we have R1 parallel to R2, wherein we have 4 times 2 divided by 4 plus 2. So 8 divided by 6 is equal to 1.33. So this one is 1.33 ohms. 1.33 ohms. And then for the R total, we have here the R1 parallel to R2 plus R3. So R1 parallel to R2 is 1.33 plus R3 is 1 ohm. So this one is 2.33. And then for the B total, it's still 7. And then RT is 2.33 ohms. So 7 divided by 2.233 is 3 amps. All right. So we will stop here for now since we don't have enough time anymore. So we will just continue the rest on the part 2. Okay, so goodbye for now and see you guys later.